also for joining us. Our last session of this third theme on stochastic modeling and pricing and revenue management. The details for the fourth theme are on the website, and you will be receiving one more email from me concerning all the details. Today, I'll be presenting a recent paper that, based on mainly a recent paper with my co-author, René Caldente from the University of Chicago. And basically, the topic I want to talk about is a continuation of learning that started with Arnaud on the short course, but focus on more Bayesian approach and also a different type of tool, basically relying on diffusion approximation. So to some extent, two not novelties, but differentiator with the typical approach that Arnaud discussed in the last three sessions. And so Bayesian and the diffusion approximation. I'm gonna start with some, anchoring slide. Make sure that, some terms are clear. I will talk a little bit about one of the motivating, in some sense, application that we had in mind, and then mention the outline of the talk, and then go into the details from there. So basically, when we talk about sequential testing, it's really the advantage of it is the fact that you don't need to set your sample size when you're testing or experimenting, ex ante, right? So it's a dynamic way of deciding on the sample size, meaning that as you get more information, you realize whether this is enough, and so why continue. Or in fact, it's not enough. And in this case, you will keep on getting more data until you feel satisfied. So really, there are three decisions. Continue experiment at the result of every outcome of an experiment or a test. Either you continue experimenting or you stop. And in this case, you either discard, basically you pick the null hypothesis, or you adopt, and that is picking the hypothesis you're testing. The example that I picked is in hypothesis testing, but sequential testing is broader than this. But embedded into that is a trade-off between time and the experimentation. So kind of the exploration-exploitation type trade-off that again was present and discussed by Arnaud on the first session. Right. So you would like to spend more time to learn, but that's kind of costly or delaying some implementation, which is a bad thing. And you don't want to implement that too fast, because you will be missing maybe on some information, and you will be basically executing or implementing the wrong solution. Like all the other sessions, please, this is a casual talk. So feel free to interrupt me or write on the chat, and I'll read the question to everyone, but to otherwise unmute and ask your question. Basically, this is not a new thing. Of course, sequential hypothesis testing dates back to Abraham Wald in the 40s. It has plenty of applications in manufacturing and quality control, a lot on healthcare and clinical trials, but also, let's say, computerized testing, where you have some dynamic testing approach to basically have it more customized to the person taking the test. But I'm just mentioning these, but there are plenty of other types of application, and this talk will actually also introduce another type of application. Since Wald, we know that sequential probability ratio test is an optimal stopping criteria. Again, in sequential testing, there is an optimal stopping problem by definition, by structure. And so the question is, what is the optimal stopping? And basically, Wald, under some first assumption, basically came up with an extremely simple and beautiful solution to the problem that eventually, was proven to be optimal. Now, many variants of sequential testing. Basically, we have optimal or asymptotic optimal solutions for these, and a lot of the times the proofs are based on large sample size. So basically, letting time goes for some time, and in particular, letting the cost of experimentation becoming smaller and smaller. Now, the title of this talk is about sequential experimentation. What is the difference between sequential testing and sequential experimentation? Basically, sequential experimentation is more complex because at every step, you're not only deciding whether to continue experimenting or to stop, discard, and adopt, but also to decide on which experiment to use. So it's not like one type of experiment, but you can have a number of experiments available to you, and you can pick at every time one from this bag of experimentation. All right, so this is just background terms to be familiar with. If there is any question, please feel free to ask it at this. All right, so some recent players of experimentation actually are these major players today in the tech world and in online world. Basically, these guys have invested amazing capabilities. So a lot of money has been spent on building and hiring, data analysts or computer scientists and so on to actually try to experiment using that platform in order to improve the customer's journey. Right, so you can use it, for example, at Airbnb to pricing. You can select a type of one price for a do some kind of A/B testing for a population A, and population B use another price and see how things work. So basically, this type of experimentation is a huge development and being used a lot at these companies. This is actually a recent issue of Harvard Business Review that talk about the exponential growth of experimentation, at different major players, whether Amazon, and in this case, the picture is showing Bing, where they're really using this experimentation because there's a lot of traffic, people are coming in, and they're basically using that traffic to test whether you know it or not as a visitor, but you're basically being used sometimes in those experimentation. Just to give you an example, even like the type of blue color at Microsoft has been basically adjusted based on experimentation, right? So they will show some people one type of blue, other people another blue, and they will see which ones are basically spending more time, distributionally on the website, and then they will conclude on which is the best type of blue to use. One particular application that is of interest to us here is crowd voting. So crowd voting is as part of this crowdsourcing, whereby you're going to the crowd, and that's a very old approach. Babylonian times, I think they when someone was sick and they didn't know what he or she had, they would leave him in the middle of the village, just so that in case someone is passing by who actually would recognize this disease, and they will basically maybe help him or her because no one was able to to recognize what kind of disease this person had. So crowdsourcing is going to the crowd and asking them for help about a particular problem. Again, the list of companies that is using this is incredibly increasing, using platform to kind of like really make sure that customers are happy with the new product is now more typical or more the rule than the exception. Mentioning here Lego, Amazon, and the fashion industry and so on. All right, so basically what we want is to to think about this type of of online experimentation as a sequential testing program. So I'm calling this not the outline but components of the talk, and I would say why. Basically, what I would like to do in this talk is talk a little bit about modeling. Indeed, because there is an interesting application and an interesting problem, and kind of defining the ingredients, the new ingredients to an old problem. I'm going to talk about diffusion approximation and some special scaling. I'm going to find the time to talk about the mathematical solution and ideas as proofs, and these are really meant for people that are not in the area really. Because I'm not going to go into details of proofs, or PhD students try to see what kind of machinery or type of mathematics we use. And by no means I'm going to really go into any rigorous detailed proof here. And the objective is to talk about some managerial insights and numerical analysis. I will be, depending on time, I will push this or not, because that's not my main priority here. This is a published paper, so you will see at the end the list of papers, and you can maybe Google it or drop me an email. I will share it with you. So where we talk a lot about managerial insights and other things. And also I would like to leave some time to talk about similar type of scaling for a very recent also work in a slightly different context, which is still experimentation, but related to multi-armed bandit. And that's not my work, but other people's work. All right, so given that, I'm gonna anchor you with an example and then set up the problem after that. The example is the following. Suppose you have a number of designs, right? Plenty of designs. So there's a company that's called threadless.com, is threadless.com, is based out of Chicago, where basically, you have a nice design, you will basically send them, share it with them. And then that design will be put on a website. If people vote on this design and you have enough votes, then your design will be printed on t-shirts and will be sold, and you will make money. Okay, so we can imagine here a setup where we have a lot of designs, hundreds maybe, or tens. And the question is, which one is the favorite, right? Or some top rank. I'm just anchoring you, but I will set up the problem a little bit later mathematically. So the idea is, let's ask people to actually select their favorite. And so Renee will show up on this website, and then the platform will decide to show Renee one set, right? So an assortment based on the terminology that Arnaud defined yesterday, one assortment, and before in the MNL discussion, basically, right, of t-shirts. That is an experiment, because as a result of that, Renee will decide to vote, maybe not vote as well. So that will be, a choice of not voting, right? Or voting on one t-shirt. I will show up, and I will show me another set of t-shirts, and I will select one. Jihad will show up later, and then we'll show Jihad another set of t-shirts, and then he will pick one. And then we decide that this is the stopping time. We learned enough at this point, and we're gonna stop and make a decision. And so our problem is, in this example, the problem here is to find a learning policy that allows us to learn as quickly as possible, basically the best choice. Okay. So notice that, here, for example, the idea could be to select from the original set of t-shirt a subset that you will, sell or put in the boutique for sale. Now, let me write the mathematical formulation of our problem, which is slightly more general in some ways and more restrictive in others. So we have a decision maker that has to choose an action A. And that action A, for example, is which subset of, let's say, t-shirts I need to commercialize. And if I decide this, then I will generate a reward. That reward depends on my choice of course A, but also depends on some unknown parameter theta. That parameter can be even a density function, or just values. For example, it could be the price sensitivity of my customer. I don't know their price sensitivity, but basically, it's a random for me. I think that the price sensitivity takes two values, theta 0 or theta 1. But I can also experiment to learn this. And so I'm going to run a set of sequential experiments. And for that, I have a set of experiments. So what are the set of experiments in the previous example? Any subset of the total number of designs or the total designs is an experiment, because I need to decide which set to show to an arrival. As a result of that experiment, there will be an outcome, right? The outcome is some value X. And assuming I know the distribution on X conditioned on the value of theta. So if theta equal to theta 0, so otherwise, if I see an outcome X, I know what's the probability of seeing X if theta equal theta 0. Of course, I don't know theta, but if theta equal theta 0, I know exactly the distribution of seeing that outcome, or the probability of seeing that outcome. And if theta equal theta 1, I also know that distribution. And so I'll be seeing outcomes, but basically I don't know from which distribution they're coming because I don't know the value of theta. And so I'll measure the information of that outcome by taking the ratio of these two probabilities or these two values, the probability of seeing this outcome given theta equal theta 1, divided by the probability of seeing this outcome given that theta equal theta 0. Aiden, go ahead, please.
Hi, Victor. So can we separate a non-response from non-choice? As in, like I show you, let's say on Netflix, 5 movies, but at the time you really didn't have time, so you didn't give a response. No. Versus in other situation, I showed you 5 videos, 5 movies, you didn't like any of them, therefore you didn't respond. Right?
No, here we can, but I mean there are indeed some studies that will try to take. I mean, this is a typical problem in practice, right? So there are indeed some statistical way to kind of some sense guess the proportion of those, right? Not really which one is. We'll never know, right? But here, no, we're not this. So because just to make the answer simple, here we're assuming that if you don't choose, then that means you chose nothing.
Great, thanks for the clarification.
Yeah. And so the information is the ratio between these two values. And what is my policy is quite complex one. I need to decide for every, some sense, visitor in the anchoring example, right? So I need to decide which experiment to use every time, when to stop, and when I stop, what is the optimal decision to make? Okay, so indeed, for example, this is much broader than the class of multi-armed bandit problems, because or best arm identification, because in best arm identification you need to decide what is the optimal arm, in case you're familiar with that literature. While here your decision is in a space different than your space of experimentation. However, here also we have one uncertainty, and in this specific paper, this uncertainty theta takes 2 values. So what's the formulation? Basically a high-level formulation. It will be more detailed and more correct. This is not, there's something hiding still, but at a high level, what we have is an optimization on this policy. So it's a very, kind of complex space of policies, whereby I'm trying to maximize my reward, but discounted because I want to introduce time. I want that, I don't want to take all my time to learn. And so I want to, introduce this exploration type trade-off to some extent. I mean, it's really an exploration problem, but then with the cost of delay of the reward. And so I'm discounting the reward. And so I have every single interest to learn as fast as possible so that I generate the reward as early as possible. Right? But of course, I want to try to learn as much as I can as well. All right. So the problem here is, or the objective function is a discounted reward that I'm trying to maximize. All right. Now, I talked about online experimentation. So what is new here? Of course, we can find many or a long list of differentiator between online experimentation and typical experimentation. I'm identifying 4 that I think are interesting. First, the cost of experimentation. The first one is a good news to us. It simplifies our problem. The cost of experimentation in online is free. Basically, the variable cost is 0, right? There's a visitor coming in, seeing in a display set and choosing, right? However, the experiments happen at some kind of stochastic process, of arrivals, right? Because I don't decide when the experiment is going to happen. It's going to happen, let's say, when you arrive to the website. So we're going to assume, for simplicity, which is a typical assumption, that we have a Poisson process of arrivals of visitors to the website. Right? And then basically, we expect that we can have a high number of experiments here because of the traffic. So we expect the rate of the Poisson to be large. However, the bad news is that we also expect that this experiment's outcome not to be, very, precise, but rather very noisy, because we don't know who's voting. We don't know how serious. This is linked to Aidan's question. We don't know whether you chose because, not to vote because you didn't like any of these, or because, for example, you didn't have time, right? So there's plenty of noise that is there. We don't even know whether there is a computer voting or a real person behind it, right? And so the information that we get out of so-called experiment should be extremely, low. For now, I'm explaining the space of policies larger than the bandit problem. Yes. So let me go back here. So basically, in a bandit problem, first, a multi-armed bandit problem is one where you have a horizon, let's say T, and you need to decide which arm to select. The arm is an experiment, and the experiment generates revenue. It could be in our setting like a cost, right? But basically there is a revenue generated out of an arm, and then you need to minimize the regret or maximize the reward that you're making during this horizon. There is something, kind of related to that problem, and that is called the best arm identification, where you play some arms for free, let's say, and then at some point in time, you need to stop and select the best arm, and your problem ends here. Basically, your set of experiments is the arms, and the choice at the end is also one of those arms. In this problem, the choice at the end is not necessarily one of those arms. I hope this is clear, Ali Reza. Right? So basically, the optimization at the end could be from a different set than your original set of experiments. So I don't need to pick, among the t-shirt design that I used to learn from. I could actually, decide on another one. All right. So for now, I'm just going to be focusing on these two. It's easy to incorporate this. First, the cost of experimentation. Basically, there's no cost of experimenting. And so second one, there's going to be a Poisson process of, governing the learning process. So let's move to the learning. On the learning, we have, as I said, a Poisson process. And then I have a random variable, theta, that can take two values, either theta 0 or theta 1. I have a prior because I'm going to do Bayesian learning. So for example, I have that some value, let's say 0.5, that probability that theta equal theta 0. And my aim is to keep on updating and learning on that probability, on that what I'm going to call the belief, and that's your delta t. Okay, so delta t is the probability that theta equal to theta 0, given all the history that you have up to time t. All right, this is a stochastic process. By construction, actually, it's the so-called, it's a Martingale process. All right, we can show, that's not too difficult. I'll show you in a second. No, it's not a continuous version of a best arm identification. But let's come back to, if you don't mind, to bandit relationship later. Okay, this is basically again, depends on what you mean by a continuous version of best arm, because usually the continuous version is you have a continuous number of arms. Okay, here we don't have that, but there's a continuous time of when you're playing, when you're picking the arms. But it's still a discrete problem of experimentation, but then the continuous time is from the fact of when you're pulling arms. Okay, so again, let's focus on this, and then we'll come back to other versions later. I had in mind to talk a little bit about the multi-armed bandit later. All right, so what do we have here? We have basically a arrival process Poisson. For every arrival, we have an experiment. This experiment allows us to learn, and then we can update our belief process, delta t. We can show that this delta t follows an SDE of this form, governed by the Poisson process. And then with a multiplicative term, that multiplicative term, you know, it looks ugly, but in fact, it's quite intuitive. Basically, it's driven by the information L, which is the ratio of the two probabilities that I mentioned earlier, right? So if, let me show you also how it looks. It looks like this. So it's a jump process. It's also a Markovian process. And so at every experiment governed by the Poisson, right? So the timing of the jumps is driven by the Poisson, and the jump is driven by eta, by this, okay? And so these jumps, if basically the information you got is telling you something more positive with respect to theta 0, the jump is gonna go up, right? So L is gonna be strictly less than 1. And if the information you got or the outcome from the experiment is telling you something that you're actually closer to theta 1, then in fact the L will be larger than 1 and the jump will be negative. This is a bounded martingale, so we know that it's converging almost surely. So if you wait a lot of time, you're gonna converge either to 1 or to 0. Okay, in this path, we're converging to 1, or in this setup. All right, clear? Any question on that? This is basically one of the main ingredient, so it has to be clear to everyone for the rest. Any question here? All right. So quickly, how do we get this? But again, this is mainly for people that are not necessarily in the field. We're basically using Bayesian rule from the definition of delta t. So I'm looking at delta t at the time of an experiment. And at the time of the experiment is basically equal to the probability that theta equal to theta 0, knowing my entire filtration. And by applying the Bayesian rule, then basically I divide it into this way. I flip the probability. Now, this term is just delta t minus 1, right? Because basically this is a condition on the filtration without the last outcome. This one is given by exactly Q. And I can also write the same way 1 minus delta t, which is the, for a condition, given theta equal theta 1. Same thing, but applying the same Bayesian rule. The only difference will be that I have a Q with theta 1 and the other one will have Q with theta 0. And I'll take the ratio between these two. And by taking the ratio of these two, I'll appear this likelihood function that I mentioned earlier, and some recurrence that I can iterate. And by iterating, then I can show that delta ti is in fact equal to my initial value, delta. Oops, sorry with that. Okay. And then introducing the product of the likelihood function of the different values, right? So the history is there in the delta t. Okay. And given that this is actually a pure jump process, then in fact, we can have exactly we can replace delta ti by delta t because the value of delta is not changing between two experiments. Now, I want an SDE. Everything I do is I write delta t as a, some function of a nice random variable. And then I apply Ito's lemma. And then, we get this SDE before. Okay. So basically, a more correct problem formulation is the following. I am looking at, coming up of my profit function with respect to a prior delta, which is an optimization of an expected, discounted reward, where my policy is to find the experiments, the set of experiments, the optimal stopping, and the action A. Now, given that the action A is happening when I stop, I can always introduce this function G of delta. That is basically, the maximization that's going to happen once I stop. Of course, once I stop, it's going to depend on, the value of delta at that time. So it's delta of tau, tau being the stopping time. Okay. I'm keeping the notation pi, even though now pi is the experimentation and the stopping, and A is left for later. All right, so we have that problem to optimize. It's quite complex. I can try to write what we call the AGB equation, Hamilton-Jacobi-Bellman equation, which is dynamic programming to some extent. Is, for those that are not very familiar, is a way of turning this stochastic optimization, quite complex here, into a no-DE if I have a finite horizon. This problem is a kind of an infinite horizon problem, so I get a fixed point equation to solve. But most importantly, again, for those not very familiar with that technology of dynamic programming, you're turning a problem, of solving on this set of policies space into a problem of finding pi, what we call the value function, right? So we're trying to find f, not x star, right? So if I'm trying to maximize f of x, I don't try to find directly x star, I'm trying to find the function f, and then from there, I can obtain x star. Right? Extremely powerful approach, but everything it tells me is some, equation to try to solve, which is extremely hard. I can solve it numerically through, different ways. For example, an effective way is value iteration. And once I have that, I can, once I solve for pi, then I will pick the experiment at any time t that maximize this quantity, right? Because, you can see from here that if I know the value function pi, right? If I know this black box, then I can find the experiment. Of course, finding the pi is the hard thing, but as I said, we can solve it numerically through value iterations. Okay, and so here I'm showing you numerically that in fact there's no necessarily clear structure for that. These are numbers, kind of a Mickey Mouse example with non-experiments. Every experiment is basically there is an outcome that is either 0 or 1. So it's like a coin. And then there's 2 coins, one with theta 0 and one theta 1. In this experiment, sorry, there is to some extent 18 coins, right? So, every experiment is 2 coins. I don't know which one we're flipping. The real system knows, but not you, right? It's beyond the scope of how we derive an AGB, but basically you basically need to look at what happens in dt, and to some extent in dt you have an arrival with a rate lambda tt, and given that arrival, you basically have either a jump up or down, and that's going to affect your value of function by this eta. But really, it's beyond the scope here how they derive an AGB. But I just wanted to say that you could do something without moving to approximation, which is our objective in this talk, right? So I want to try to move to to the main meat and the main objective of the talk, and that is approximations of such value function. All right, so back to the numerics. Here I have 9 experiments, and experiments basically, here, if I see a 0, then it has 10% chance that's coming from from theta equal theta 0 coin, and 3% chance that's coming from a coin where theta equal theta 1. Right? If I use experiment 2 and I see a 0, then it has 20% that is coming from theta 0, and 4% chance that's coming from a coin of theta 1. Of course, these two should not sum up to 1, right? Because these are two different coins. But what is interesting is here is that solving the problem that I showed you earlier shows us that, in fact, there is dynamic experimentation, that depending on how delta, the belief process, is changing through time, you might pick one experiment or the other. Right? So the vertical axis of this graph is the 9 experiments, and the horizontal axis is the value of the belief. So you can think of the horizontal axis as time, or linked to time, right? And delta t is moving through time on this horizontal axis. And for every value of delta t, you will pick the experiment that is optimal at this point, having solved, your problem and having the optimal policy. Okay. So again, the AGB was only used to solve this numerically. But again, that's not our approach. Our approach is to come up with approximation for this complex problem. Quite intractable. And one way to do that, again, most of the literature related to experimentation is to try to find some asymptotic analysis. And who says asymptotic? You're making, you're working in some regime, you're scaling things. Okay. And the question becomes which regime. So at this point, I want to, remind you of the online experimentation features. We already discussed cost of experimentation and the fact that arrivals are happening through Poisson process. These other two features are going to be used to define the regime, right? We are in a setup where there's a lot of frequency. So indeed, large sample size is going to be there. That's expected. And we're going to do that by increasing the rates of the Poisson. Of course, I'll define mathematically exactly all this. And then the fact that experiments are noisy, we're going to work in a regime where there is low informativeness. And that is, in our terminology, the likelihood function close to 1. Right? So the jumps are very small, right, of that Cadillac process, of that belief process. Okay. So we want to try to reconcile this by the regime. In some sense, this is kind of the motivation behind the regime I would like to discuss. Here, I want to open another bracket for, again, those that are new to this field, trying, to see what's driving the machinery that we're going to be thinking. And so our objective is to approximate delta t. This is the beast, the main beast that is ugly. It's a Martingale and a Markov process. So let's step back and then, look at probability theory, or simple probability theory. We know that if you consider, for example, a random walk, a simple Markov chain and a Martingale, or a sub-Martingale, super Martingale, depending on the size, the drift, right? That random walk with a mean mu and variance sigma square, we have very powerful, results or around that. One is the strong law of large number that tells us that, the arithmetic average is going to converge almost surely in an extremely powerful way to the mean of the increment of x. And more interestingly, kind of a second order approximation, that in fact, if you center that random walk and you scale it by square root of n, then in fact, it converges weakly, whatever this means is by law, the law of Sn minus n mu over square root of n, to a normal random variable. And practically speaking, you're actually, we're basically smoothing out the jumps of the random walk, right? And we have a nice, now a continuous random variable, somehow a normal distribution with mean n mu and variance sigma n sigma 2. Okay. Now we can actually do that with random walk-like processes in a continuous time. So we can actually introduce S at index nt. Now we're actually introducing a much more complex item or ingredient or random entity. We can also show what we call a functional strong law of large number, that if you let n goes to infinity, then that stochastic process is going to converge to mu-t. But more interestingly, and much more complex to prove, that's Donsker theorem, that in fact, the stochastic process defined as SNT, so S at the integer value of NT, minus, so centered n mu-t, divided by square root of n, will converge to actually a Brownian motion. Right? And here, the machinery is much more complex because now we are in a space of, Cadillac processes in this case here, and we need some, define the right distance to define the convergence, and we're converging to a process that's quite ugly, that is not, non-differentiable everywhere, and so on. So this is obviously much more complex machinery than this one, but both of them are driving us into the same idea that I'm trying to smooth out a process that has jumps. The random walk originally had jumps, and now I'm actually trying to smooth it out. And Brownian motion has a lot of nice properties. I want to take advantage of that. Right? So that's basically what's going to drive us to define diffusion approximation, rather than, in some sense, fluid type approximation driven by law of large number or concentration inequalities. So back to our problem. I have this belief process. I said it's a Markov process. And what I would like to do is to try to actually smooth out this jump so that I basically make it converge to a diffusion process. That's the approach. And so what I want is to scale the rate of the process here, right? Like we scale in the central limit theorem, by n, and then, or we want to, scale the space by square root of n. Here we're gonna smooth out the jumps by letting L close to 1, right? And the jumps, the size of the jumps are governed by eta. All right, that's the idea. Any question? All right. I'm calling this the online asymptotic regime, just because it's driven by this, kind of features of the online experimentation. All right. So to do that, I'm going to introduce a parameter k and define a system parameterized by k. So the system being the optimization problem that I defined, right? So basically, let me just go back again for those not familiar with this type of approach. Here I have a black box, and I'm going to parameterize this problem by k. Right? So I'm going to have pi k of delta, where in this problem, k will appear as I'm mentioning now. So the rate of the Poisson will be, scaled by k. So system k will have, k times lambda rate. Say system k plus 1 will have rate of the Poisson, k plus 1 lambda. And then what I want is to scale down the informativeness of the experiment concurrently, right? So that's the main idea, or the main, in some sense, novelty of this diffusion approximation scaling, is that we're scaling two things at the same time. And so how am I going to do that? I'm going to basically have the likelihood function Lk, which is really just the ratio of the two probabilities. Remember that probabilities Q are my primitives. This is what I'm given. So every system will have, Qk for theta 1 and a Qk for theta 0. And what I want is the ratio is close to 1 with some error of 1 over square root of k. Now, okay, why is that? It's just so that I get my diffusion approximation, right? The whole, in some sense, design of the scaling is to create, in a way, something that when we let k goes to infinity, you converge to something that makes sense. Okay? And so what is interesting here is that, of course, if I scale only lambda by k, what's going to happen? I'm going to have so many experiments so quickly that I'm going to learn in a fraction of a second, and the problem is obvious. Right? So the idea here is to actually scale lambda, but at the same time, for system K, the informativeness is so low that I'm not learning much from each experiment. So that when I put them together, that basically if you want, the learning per unit of time is kept the same. But something is nicer or more tractable will happen as we do that, right? So to some extent, the limit here, as opposed to, typical literature where we let just the horizon goes to infinity, and when we let the horizon goes to infinity, we know that we're gonna learn, right? So what we try to do, we try to control the error of the regret or something like this. While here, at the limit, we still have a problem where we don't know what's the optimal solution is, as you will see in a second. So specifically, I'm going to write this LK to be 1 plus 1 plus capital O of 1 over square root of K of the following sense. This probability for every theta is some probability that does not depend on theta, right? So pure noise, right? If I tell you that the Q that this outcome that you see is independent of theta, that means you cannot learn anything about theta, right? So, what we're saying is that the Q that you have is a Q that does not depend on theta times a term that depends on theta, but discounted by square root of K. So as K goes to infinity, you basically get to a system where it's pure noise. Every vote is noise, nothing. You don't learn anything at K equal to infinity alone. Okay? But of course, you're not going to let this go to infinity alone. You're going to let this go to infinity at the same time of this. So hopefully at the limit, you have something quite interesting happen. All right. Any question here? All right. So this is the noisy experiment. Those that are working in queuing theory or are familiar with that literature, this is, for example, something we typically do in queuing theory to determine, for example, again, some tractability of queuing system that could be quite complex, whether network of queues or single server queues. And the so-called heavy traffic is a way to actually scale arrival rate and processing time in a way that you basically have balanced loading, but at the same time, tractability of the queuing system. And so we're, to some extent, bringing some of those ideas in the context of sequential testing. All right, so reminding you here the scaling we did, right? So we're scaling concurrently the time or the rate of the Poisson and the informativeness in this specific way. And I'm reminding you the belief process SDE. And then the first main result shows that, in fact, this belief process that is quite ugly converged to a diffusion process with an SDE governed by a Brownian motion. So it's a diffusion process. All right. We have in closed form this instantaneous variance. So we know it in closed form. I'm not showing it here. That will depend on those alpha, of course. All right. So how do we prove something like this? We actually prove it in two ways. In the paper, there's only one way. But also, again, it's a bracket and opportunity for those that are interested in this type of literature to get an ideas of the machinery rather than any, again, rigorous proof here. Okay. The first approach will be, which we actually follow in the final version of the paper, and that is, driven by the Martingale framework of Strouk and Varadan, that is applied to Markov processes. And to some extent, what we're doing is actually coming up with a generator of AK, generator defined this way, where this K is the kernel of the Markov process. Again, this is a Markov process, so it has some kind of transition kernel. And so we can define this generator this way, applied to functions that are nice, bounded functions in C2, for example. And so that generator will actually make that term a martingale. And now what you need to show is that to some extent, infinitesimal mean and variance of the stochastic process converge to infinitesimal mean, in this case 0, because it's a martingale, and the infinitesimal mean of the diffusion that we obtain at the limit. And then you need to handle some tightness condition, which is usually the tricky part. But in our case, because it's a simpler, and this framework is really extremely general, basically showing these tightness are not very hard to do. Right? So there's a major machinery that you can implement, or you can go from first principles. And in general, first principles is like, a little bit of luck and trying to manage basically what you have, building on the fact that you have a, Poisson process, in some sense, the ingredients that you use in general is some kind of CLT for Martingale and the continuous mapping theory, right? To some extent, these are two major building blocks that you put together to obtain your limit. Okay, it's a bracket just giving you a feeling of the type of math that is behind this. All right, so back to our problem. We already showed that our belief process, which was a Cadillac with jumps and quite complex jumps, can actually be, approximated as k goes to infinity, of course, but that's the asymptotic approximation. We're using what we get at the limit, basically as the dynamics. So we're looking at the limit, what would be our formulation of the problem? And the formulation of the problem from an objective function is the same, but the dynamics are basically now a smooth process. Right? But again, extremely different than typical literature. Now the limit is not just an obvious thing, right? We didn't learn everything just by, right? We're at the limit, we have still a problem to solve. We still have a belief process and a stopping time and an experimentation problem. However, things are nicer. Indeed, we can solve that problem fully. First, we can prove that at the limit, that's really something we didn't expect, that we can decouple the experimentation problem from the optimal stopping problem. Meaning that finding the optimal experimentation policy is independent of the optimal stopping problem. And so once you solve this, you can feed it into an optimal stopping problem kind of black box and solve the optimal stopping problem. That's number one. Number two, we show, and there is a good news and a bad news. The good news is that we can solve exactly what's the optimal experimentation policy. The bad news, or bad news in some sense, the disappointment here is that I basically expected a dynamic experimentation, and at the limit, of course, because we're smoothing out things, then at the limit, the optimal experimentation is static, meaning that there is one experiment that maximizes your basically optimization problem. Okay? And of course, this is not going to be, in some sense, acceptable maybe, and we want to improve on this as an approximation to the real problem, to the non-asymptotic basically regime. But at the limits, the static experimentation is optimal. And we can have a closed form of that experiment, by solving that problem. We know alphas, we know the Q, and so we just need to find that experiment. In this general setup, this optimization, could be quite, we could have a combinatorial problem here because it's all finite set. But in a setup of, in a particular setup that we, consider in the paper related to product assortment and product introduction, we actually can show that this optimization is tractable, and we don't have a curse of dimensionality. All right. So basically, this is saying that pick the experiment that maximize the volatility of the learning process. Quite intuitive once you see it. But it's not true in general. It's at the limit that it's true. Okay, and that's why we're calling this proposition the maximum volatility proposition. Right? So pick the experiment that maximize the volatility of your diffusion process. So I have a question: why the separation principle holds? Yeah, I I have to say, this is Bo, you know, I was trying to think of intuition before starting on the talk, because I was to some extent expecting this this analysis, this question to some extent. One way to see it is, to some extent, there is the proof of it comes from the fact that you can do a time change here, so kind of a change of variable that will make the sigma appear in the exponent of the exponential. So if you do a change of variable, in fact, you will end up with a problem where basically there is no more experiment in the dynamics of the belief, but the experiments only appear in the exponent of the exponential. And so what you want now is to maximize your profit, and that means you want to maximize, because maximize the sigma, and so you will pick the experiment that maximize the sigma, and the belief of the process will actually will be independent as a result of this change of variable of that experiment policy. Is it clear? It's a kind of trick that we notice if you try to prove it in a brute force. It's an extremely difficult problem to actually try to solve it, right? But with this trick of change of variable, it's actually quite obvious. Okay, good. So given that, we show that there is a static experimentation. All right. So numerically, I'm revisiting the previous example that I showed you earlier. Now we could reduce, and this is in the paper discussed, the experiments. I had 9 earlier, now I have 6, because some other experiments are basically, we know they're inefficient to some extent, and we have a way to say that this experiment, you should not be using it. I'm not going into details there as a result of some concavity result or convexity result of the value function. But I'm revisiting that process, and I'm basically building up on this asymptotic analysis. And indeed, by introducing this kind of calq that doesn't depend on theta and building this likelihood function that depends on theta just through this term, we indeed see that as k becomes large, the optimal policy is static. Right? All right. Now I still have to solve for my optimal stopping problem. Now, here again is going to take me too much time to explain this. I'm just going to give you an idea of the solution approach, right? So now that we solve for the experiment, we need to solve for an optimal stopping problem. And interestingly enough, we can actually solve it in a nice way. We fully characterize it. And the trick is to start, one of the complexity of this is that we have here a reward function that depends on space A that I defined earlier. So the action, or if you want the assortment you're going to select at the end in the anchoring example, can be quite large. And so the trick is to start with a problem where you only have 2 actions at the end. So when I stop, I only have 2 actions. And in this case, we can actually solve this problem exactly, meaning we characterize the continuation region and the stopping region. And for this, we follow the so-called quasi-variational inequalities, but really it's about some, getting some ODEs that you're trying to solve, and what we call the verification theorem, meaning that you come up with a solution of the problem and you verify that it works. Right? So in some sense, how we solve sometimes ODEs, basically you feel that this is the type of solution, you put it there, and you notice that, yeah, it works, and you can show its unique one. And then once we do that, I'm not showing you the characterization, it's in the paper, it's quite ugly. You actually show that the optimal, basically, value function you're looking for is in fact a maximization on all value function for a, kind of a 2 action, for any 2 action that you would consider. So you will just take the envelope on, the different problems of, 2 products at a time. Okay, and again, this is the complexity is in the size of the kind of the products or the size of the action space A squared, so it's not that bad. All right. Again, just a feeling of things, right? So I'm solving an optimal stopping problem by reducing the problem to basically a reward function that is driven by a two action. And then I take the maximum of that solution on all, two action possible. Usually so I have a question. Usually the AGB in optimal stopping is an optimal stopping is a VI, stochastic impulsive control. Yeah, I got that, the variation. Why the pure optimal stopping is a QVI here. Yeah, that's a good point, but I wouldn't be able to answer like this. I mean, it's a free boundary problem, but maybe we can talk at the end if you're interested more. But honestly, I will not be able to say that detail here like this. That's a good point. All right. All right. So basically, I have these two formulation of the problem. This is the original formulation. And this one is the diffusion, in some sense, version of it. The main difference is that those dynamic here is following the diffusion process. Okay. And now the approximation I'm going to select. First, I can select an approximation that is driven only by this one, whereby I pick the static experimentation that is solving the diffusion problem. And then I will stop following exactly the stopping time driven by the diffusion problem, which I can solve, also nicely, as I mentioned earlier. But that will give me a static experimentation. And this is a little bit, kind of disappointing, as I said. Or what we're calling the maximum volatility. And what is this maximum volatility? Is basically an experimentation that is at every time t will pick the experiment that maximizes the volatility of the original problem, right? So in other words, of that jump here. Okay, so I'll pick at every time t the experiment that maximizes that jump function. And now I don't have a static experimentation here. It's a dynamic experimentation. However, for again tractability, I will use the stopping time of the diffusion problem again because it's simpler to handle. Right? I can obtain it for any experiment. So before I show you some numerical result that show you how actually quite powerful this one is, let me just open a bracket because I really like this bracket and I think it's always good to think about the real problem. What I'm calling this slide is the interpretation of the asymptotic regime. For some of you, this scaling is a little bit too theoretical. The primitives of the problem are, I have a Poisson process with rate lambda. I have this probability Q for theta equal theta 0 and for theta equal theta 1. I introduced basically a scaling for the lambda K. I mean, it's kind of straightforward, but there were this other scaling that I expected the informativeness to behave this way. And I'm introducing this Q and alpha, and these are not primitives, right? So if I'm given real data, for example, I can come up with these three, but then what is this Q and alpha? And so without dwelling, basically we give a way to actually come up in a non-parametric setting, so a non-parametric model for the probability Q of the cal-Q. So the cal-Q, we define it as a solution of a min-max problem. To some extent, is the closest between Q theta 0 and Q theta 1. It's an interesting kind of bracket, so that we make sure that what we're suggesting as an approximation, we can implement it in reality, because in reality we are given those data, and we need to define that regime, and that regime is driven by these Q and alpha that we introduced in order for our math to work. All right, so we need to solve this optimization problem, and we verify that in fact it has a nice property with respect to the problem we have, and then we can come up with alpha as basically also with respect to this lambda, the primitives of the problem Q, and the cal-Q that we obtain from that optimization problem. All right. At this point, I'm going to go faster on that kind of managerial insights to leave a little bit of time to discuss also a recent paper on Multi-Armed Bandit using some similar ideas. But let me tell you just how we can implement this in a setting of assortment and new product introduction. So think of a website that is receiving basically visitors at a Poisson process with rate lambda. And each customer sees a display of products. This is our experiment, and will vote on their favorite one. What is the probability Q? The probability Q is basically going to be following some, a choice model. For example, the most typical, Arnaud mentioned this yesterday, would be an MNL, right, with some parameters. And the parameters of the MNL is usually this mu here, that is linked to the variance of the choices, right, times a utility, right? So, for example, the utility, is function of the parameter theta that is unknown. Okay, so you have your unknown theta that can take, let's say, two values, theta 0 or theta 1. And the utility of the customer, it could be linear, right? So, for example, Qi minus theta pi. Theta is unknown, but it could be also nonlinear. And the choice model, so in other words, the probability that you select one product is following an MNL. And I'm mentioning it because I think this kind of scaling could be nice. And it's, we're not aware that has been used such scaling on MNL type. MNL can be used in other setup, and maybe this kind of scaling, can inspire in other setup in the use of MNL. Now, let me show you how we scale the MNL parameter. So, of course, the Poisson process will be scaled the same way as before. This kind of L that was scaled here is reduced to scaling the parameter of the MNL in the following way. Indeed, that just means that the variance of the choice is going to be very high. And so basically very noisy as k goes to infinity. That means that it's going to be a very noisy Bayesian outcome. For k equal to infinity, it's a uniform distribution. Picking an outcome is basically just generated from a uniform distribution on all the possible outcomes you have. So I don't learn anything. And so we can show that the optimal experiment is actually is the solution of an optimization problem that is tractable, and that's important in particular in the dynamic setup because as I said, in the maximum volatility approximation, we need to do this optimization a lot of time. So it would be nice to know that this approximation is actually tractable. Let's go to some numerics. Here, what I'm showing you is basically an optimality gap between the optimal solution that we solve in a brute force and approximation of the value function of pi, following either the maximum volatility or the asymptotic, right? This is the asymptotic optimality gap. So following more a static approximation, and a more dynamic one is here. And even for k that is not very large, with a maximum volatility, the gap is actually converging to 0 extremely fast. And we look at runtime, is also way better. I mean, much faster, because there's not this curse of dimensionality that we face in the case of the value iteration to solve numerically the problem. While here with the approximation, we have a quite tractable problem to solve. So in fact, this approximation numerically with extremely general and large extensive numerical analysis shows that the optimality gap is extremely small with respect to value function. All right, before I conclude on that paper, I want to open a bracket related to a recent work, related literature. But before that, is there any question on this? All right, I have another 10 minutes before concluding. So it seems from the question I got earlier, some of you are familiar with the multi-armed bandit problem. It's an extremely interesting, exciting problem. A lot of recent research is happening around that topic. Basically, it's a sequential testing, and main idea for those that are not familiar is that, as I explained at the beginning of the talk, you have think of slots machines. You have k of them, and they don't give you similar return. If you pull one arm of a slot machine, you get a reward. The reward is driven by some distribution, and you don't know the mean of that distribution. And one of the mean of the distribution is higher than the others, but you don't know any of the means. And so the idea is to construct an algorithm that will allow you to play those arms. Of course, every time you play an arm, you generate revenue, possibly, but then not necessarily the optimal way. There is one slot that if you knew it, you would have only played it throughout that horizon. Okay, and so the idea is to find the algorithm whereby you learn, but you also exploit. In other words, you want to generate also some revenues. And so yesterday, Arnaud talked about this optimism principle. Basically, if you think that, based on certain number of, already trials, that this machine is better than everybody else, would you start playing only this one? Or from time to time, you go and check other ones that, because maybe your sample of, statistics for now is not meaningful enough, that maybe the best one is somewhere else, right? And so that's the idea of the algorithm, is always to try to actually deviate from the, kind of the myopic optimal at a particular time, from time to time. And you don't want to deviate too much, because otherwise you might be, leaving money on the table. But if you don't, you also be missing out on the optimal one. Okay. The objective there, as I said, is to find algorithms typically, that are asymptotically optimal. In what sense? You want to minimize the regret error, right? The regret between, knowing which one is the slot machine and getting the maximum possible reward, and the reward that you will get by following your own algorithm pi. And, there's a number of algorithms that actually are proven to be, between quotation, asymptotically optimal, with an error of capital O square root of n being the horizon. Some of them are, whether following a frequentist or a Bayesian approach, there is so-called QCB types, and following this kind of optimism principle, or Thompson sampling, which you will mention. I think Thompson sampling is a beautiful idea that dates back to the 30s and kind of rediscovered and reinvented in many ways and for different types of problems nowadays. At a high level, what are these algorithms, as opposed to what we've tried to do and what the next paper that I'm going to mention is trying to do? These algorithms are trying to tell you, look, you're gonna, if I let the horizon very large, you're gonna learn exactly which one, for sure, right? I mean, you know, it's like a strong law of large number. There's nothing's gonna hide. You're gonna converge almost surely if I'm giving you. It doesn't mean that your algorithm will converge necessarily, but you know, if you have infinite amount of time, then you can find an algorithm. Of course, you will try them all, you know, infinite amount of time, and you will converge. But what if you're interested in a setup where the strong law of large number didn't start kicking in, right? So the n is more moderate rather than very large. Are these algorithms gonna perform well, right? And so the idea here of this paper, and there is actually a very similar paper that were, both of them are, you know, on archive, so not published yet, but beautiful two papers that happen to also get out at the same time than ours, that is in a different setup of here is Thompson sampling, is using this kind of dual parameter type scaling. Okay, so this is by Li Fan and Peter Glynn from Stanford, whereby they're, you know, taking for clarity of exposition a two-armed bandit. X is the reward that is normally distributed with mean mu k and variance 1, and k and mu k's are unknown. They're following Thompson sampling. For those that don't know what it is, basically it does the following. Given a certain history, you actually estimate the posterior distribution, and for a normal distribution, it's not hard to show that you're trying to estimate basically mu hat, which is your estimate of mu k. And that by itself is a normal distribution with some mean and variance. The mean and the variance are, of course, function of the history of outcomes that you got. What is X is the reward that you got through time. And what is R? Bar is counting for every arm how many times you played that arm. Okay, so I basically takes 1 if arm K was selected at time I, and 0 otherwise. And so R is just counting the number of times one particular arm was selected up to this time. All right. And then the Thompson sampling says, now that you have a distribution for your estimate, mu hat 1 and mu hat 2, flip a coin based on this distribution for this mean, whichever gives you a larger number, right? It's a realization, right? So it's a path, right? You flip a coin, you get a value, then you pick that arm to play. All right? You don't pick it based on the largest mu hat 1. You actually generate a coin based on mu hat 1. Of course, the one that has higher mu hat will have probably a higher probability to occur, but of course the variance will play, you know, an important role as well. All right, so that's the typical Thompson sampling. And, you know, the approach will be in general to try to show that, again, as I said earlier, that the regret is minimized and what's the error of that regret and so on by letting, you know, the horizon goes to infinity. What they do here in this paper, they actually have a dual scaling again, whereby they scale time. So they basically, you know, define time Tj as j over n, and n is their scaling parameter. And they make the two basically at the same time that they scale time, they make the you know, the values of mu, the original one, the unknown one, close to each other, right? So it becomes a harder problem, but you have more time. So I'm increasing the horizon, but at the same time, I'm making your problem harder. Very similar to our approach in the sense that we're scaling the Poisson process earlier, and at the same time, we're making the informativeness, you know, closer to 1, which is a harder problem. And to some extent, we're keeping this kind of idea of your learning per unit of time is remaining to some extent same. So you would expect that this kind of approximation will lead to something that is better for moderate values of n. And indeed, we're going to get to diffusion. And as I mentioned earlier, diffusion approximations are done for kind of a second order approximation compared to strong law of large number or concentration inequalities like. Okay, so for example, suppose that mu2 is smaller than mu1. This is, of course, without loss of generality. Then what's the probability you're going to select the wrong arm? That's the probability that mu hat 2 is larger than mu hat 1, given the filtration or the history up to this time. And so their approach is they can write this probability. It's not very hard, but they write it in a nice way. They write it as a, in this form, gamma 2 of two processes. So R is a two-dimensional process and Y is a two-dimensional process. And gamma 2 is basically phi, which is the standard normal CDF. Rho is some function. So it's a nice continuous function, because I will need to use a continuous mapping theorem later. And what is Y? Again, R is what we said is the counting process, but now we're scaling it. And so we're scaling time by n, but scaling space by 1 over n. Clearly, this is going to be quite nice, right? Because this is more like a strong law of large number, like, limit. And this one is more like a functional central limit theorem type limit, but quite complex, because as we scale here and you realize we're multiplying quite ugly terms, right? And quite, linked random variables, right? I is a binomial, basically taking 0, 1, whether you're selecting the arm or not, and X is the reward. I'm not going to get into the detail, but this is really from first principle proof. Okay, and what they show, right? So this is what we have here. And what they show is that indeed, the dynamics of the type sound sampling, what are the dynamics, are driven by this R and this Y, right? Again, R is counting how many times you're selecting a particular following Thompson sampling. There's no optimal policy here. We're selecting the policy and we're seeing how it behaves, right? So this is allowing us to know how it behaves using SDE, diffusion processes, because they show that R and Y solve these SDE. Indeed, this term doesn't have a Brownian in it, while this one, as expected, has a Brownian term. So BK is a Brownian motion, as a standard Wiener process. All right. Again, I try to keep it at a high level to give you a flavor of this approach, and extremely different from the typical literature on Thompson sampling or on multi-armed bandit problems. Now, can we generalize this to other algorithms? It's actually quite probably expected that it will do well on sampling algorithms, but it's going to be completely different approach to think of UCB-like or Bayesian UCB-like to implement this approach too. But again, this is my feeling only. But from for sampling algorithm, that's going to be quite simple to adjust this methodology and this framework to such problem. Again, they don't solve it for two-armed bandit, but for any, at least their result can apply for k larger than 2 or for linear bandit problems. So back to our paper. What did we achieve in this talk? We basically have a general setup for online experimentation. Some kind of features that we introduce in a general, sequential experimentation problem. The solution approach is based on a diffusion approximation. In particular, the asymptotic regime is a concurrent scaling of frequency, which is the rate at which experiments are occurring, and the informativeness that is, going to 1. The theoretical result is a diffusion limit and an optimality of a static experimentation that we can solve fully, as well as the optimal stopping problem, which we can fully characterize. Some takeaways: the decoupling of experimentation and stopping problem at the limit only. This is not true if you're not at the limit. The maximum volatility, whereby the experimentation is nothing else than the one that maximizes the infinitesimal variance of the diffusion process, which is the belief process. And finally, we suggested a way to adapt our non-asymptotic regime to the asymptotic, to our asymptotic regime to the non-asymptotic one, right? By finding out this cal-q from data, suggesting a min-max optimization to do that. And then we observe numerically, quite extensive numerical analysis, that in fact, this approximation works extremely well, as opposed to, for example, solving this numerically, through value iteration or any other thing. On top of this, we get all of our managerial insight from our approach as well. The interesting next step is to look at, which we're doing right now, to a theta that is takes multiple values. We feel, and we already have a feeling from our analysis, that most of the kind of managerial insight will hold. So the maximum volatility principle should hold for theta with multiple values, but then the experiment will not be a static experimentation in this case. The optimal stopping problem is going to be a more complex one, because the continuation region now is not just an interval, but it's basically a more complex basically space, right? It's for a 3 hypothesis, for example, testing, the continuation region is going to be a 2-dimension space. And so there's going to be a curve. And when we hit this curve, we're going to stop. But kind of similar managerial insight should be holding. That's our strong feeling. With that, I'm going to stop. It's 6:30, so I'm impressed. This is probably the first talk I'm able to finish everything I wanted on time. But I'm more than happy to take questions or to schedule a time to discuss this. If you're a PhD student or interested in this topic in general, I'm more than happy to discuss it beyond today's seminar. But let's leave it now for questions first. Any questions at this point? Whether the asymptotic optimality proof is difficult, I mean, the optimal policy derived from the diffusion model should be asymptotically optimal in the original model. This is a very good point, but the answer is yes, but it's not an easy thing because, I mean, yeah, there is some measure theoretic issues there. There is a measure theoretic issues because, yeah, I mean, again, because we're letting a policy that is CADLAG converging to actually and even if your limit is static, right? I mean, basically, you don't have uniform convergence between quotation, to use kind of real analysis terms, right? So in other words, it's not because your even limit is static that in fact, for K large enough, you're going to have a static experimentation. But if you could, if you reduce a little bit your policies, set of policies, in other words, you're not allowed, for example, to take a policy on measure 0 interval, then yes, then we can prove. We don't do it in the paper because it was really beyond the scope at that point. But then you can prove that your policy is asymptotically optimal. And that will be really nice. Excellent question. But there is a measure theoretic issue. Yeah. Other questions? No worries. So one question is, so last question, and then I'll just basically let everyone go. And then for those interested in staying, I'm more than happy to stay as well. Why the scaling of increasing the time while making the problem harder, mu1 minus mu2 scaling down, so useful? It's exactly, the idea is really to kind of counterbalance one, right? So again, if you only scale one, you will get a strong law of large number type. If you scale the space as well, then you will get central limit theorem like, or diffusion like. Okay, so what you want is to scale, you know, kind of like just one and the other, so that at the limit you don't have a kind of a obvious limit, a deterministic, you know, kind of limit, right? That's the intuition behind it. That's why I also mentioned the CLT. Is it clear? All right. Thank you so much, everyone. I'm looking forward to see also all of you in our fourth theme, and we'll be receiving an email about that. Thanks again for your question and your attendance, and I hope you found this useful. Your comments are more than welcome, whether respect to the logistics, ideas, or this particular you know, talk. Have a good one, and we'll see you in mid-February with another exciting theme on platforms and revenue management. All right. Bye-bye. For those that have more questions or you want to chat, I'm more than happy to stay longer. Okay.